last class, we talked about finding critical points, and critical points are locations of possible maximum or minimum. Today, we will analyze what's going on around my critical point to see if they are maxes or mins. Okay. Now, what's going to help us do that? Well, let's recall average rate of change versus instantaneous rate of change. Let's recall kind of the statement that we could write when we're talking about average rate of change or instantaneous rate of change. If we have an average rate of change equal to 1/3, so we would say that on the interval from A to B, on average, f of x went up 1/3 of a y unit as x went to the right 1 unit. Okay? And then if we took those 2 points really, really close together, that secant slope would turn into a tangent slope. Let's just say the slope of this was 2. And we would say that the instantaneous rate of change of the function at that location is 2, or the instantaneous rate of change at x equals b, which is f prime of b, which is 2, we would say at x equals b, f of x is going up 2 y units for every 1 x unit. Okay? If I did not know anything about my function, if I didn't even have this graph, but I knew that maybe, let's just do almost everything. Close. But I knew that at a location, my tangent slope was 2, but I don't know what my function looks like. I can at least know that at 2, my function's moving up, right? Because this is a positive value, then we would say at that moment, my y's are going up. Just like over a interval, my y's went up on average. At a specific spot, we know I'm going up. Or if this value is negative, I know I'd be going down. So the sign of my derivative tells me if I'm going up or down. You could see that with this graph here. Let's find out when the tangent slopes are positive, when they're negative, and when they're 0. So go ahead and sketch this and just kind of use pluses and minuses for when the tangent slopes are positive, when they're negative, when they're 0. We know they are positive, getting less positive, till we hit a 0 right here. And then we have less negative, more negative, less negative, until I hit another 0 tangent slope here. And then we have positive, getting more positive, right? Well, if I look at this function from left to right, when my tangent slopes are positive, my function is going up. It's increasing. When my tangent slopes are negative, my function is going down. It's decreasing. And when it's 0, we're just kind of stopped. What we're going to do is we're not even going to be given the function. Just like on your homework problems, you're going to just be given maybe an expression. And you're not going to know what this looks like. okay? But maybe you get, f of x is equal to some x cubed. Well, we're going to find the critical points by setting it equal to 0, the derivative equal to 0, seeing when it's undefined. But then instead of worrying about kind of the two-dimensional, we'll just be able to put down the critical points on a number line, and then we'll be able to analyze the signs of f prime. And when the sign of f prime is positive, I'll say my function is increasing. When the signs of f prime is negative, I'll say my function is decreasing. And when my sign of f prime is positive, I'll say my function is increasing. This will be able to tell me that at x equals -1, that critical point actually is a max. Because think about if a function goes from increasing to decreasing, you have a max. If I go from decreasing to increasing, this will be the location of a min. And I can go ahead and almost recreate the graph without even having it, just having the original expression by analyzing the signs of the derivative. So we will be using number lines just like this a lot, and I'll show you exactly how it'll look like, okay? So from this, all of a sudden I can kind of go backwards and I could say, oh, my function probably looks something like that. Does that make sense? Okay. Well, something, and it doesn't have to be f, something is increasing if its derivative is positive. It's very important. Something will be decreasing if its derivative is negative. Something is constant or stopped, not going up or down, if its derivative equals 0. Give you a second to write those. What we will find is that when I ask you a question like, when is your velocity increasing, you're not going to look at your velocity values and see, oh, my velocity value is going up. No, it's actually going to be easier for you to just look at the derivative of velocity and see when that's positive. You don't care what the values are doing for your derivative as long as they're positive. Typically, we will say, when is f increasing? And we'll say, when f prime is positive. Now, we can denote something as being positive as being greater than 0. This is, notation for being positive. But I could ask you, when is v increasing? You would look for when v prime is positive. I could go even further and say, when is f prime increasing? What would I look to see when f prime, my tangent slope values, are increasing? I would look at f double prime and see when that's positive, okay? So it's a very important concept to see if something's going up in values. You actually just look at its derivative. If you see if something's going down, well, look at its derivative. If it's negative, it's going down because all the instantaneous rate of change would be negative. So boom, I must be going down, okay? Why do we need to know this? Understanding the signs of derivatives will help us understand where we have a relative extrema, whether critical points are going to be maxes, mins, or neither. Helps us denote critical points as maxes or mins. Really, there's 4 situations you could have at a critical point. You could either have a max, a min, or neither. This is a min, this is a max. This would both be neither a max nor a min. Now, this is what we're going to do. We're not going to be given the graph. We're going to be given an expression of x's. We will be able to find that the critical point is at the location. In this case, we'll just say the critical point's at C. But then what we will do is we will analyze the signs of your derivative around C. And in this situation, you would see that f prime would go from negative to positive through a 0, where your critical point is located. And that here will tell you that C is the location of a min, because f is going to be decreasing until C, and then f is going to be increasing, which means C is the location of a min. This is what we will be using. We will not be given this. Whoa. Trying to move the circle. Ungroup. Okay. That's what we're going to be using. So I know that for f, we have a min at C because I will create this. For this one, I will know that we will have a max at C because I will create this number line, and I will discover that f prime will be positive until C and then negative after C, which means f is going to be increasing until we get to C, then decreasing. I will then be able to say that's the location of a max. I will not be given this, but after I do this, I'll be able to create that to say, oh, my function's got to be increasing till C and then down from there. That's got to be a max. I will not be given my function, but I will be able to discover that sometimes our signs of our derivatives will not change. And when they do not change, we know we will not have a max or a min. So this is the situation where critical points aren't locations of extrema, just like that last little one that we showed on that big graphical example. Because without given this, by looking at this, I'll know my regular function is going to be increasing, flattening out to a 0. I usually put 0 right here just so I know. Flattening out to a 0 and then increasing after that. Okay, I can just kind of figure that out just by looking at the signs of my derivative. Same here, this would just be going from negative tangent slopes to a undefined location to negative tangent slopes. This is how I can say, without looking at it, oh, I'm going to be decreasing to undefined when I'm vertical and then decreasing from there. So this is the location again of neither, because f would be decreasing and then decreasing. Okay? So this whole process is kind of called the first derivative test. It just tells us that if the sign of our derivative changes, we will have a max or a min. If the sign of our derivative does not change around a critical point, we will not have a max or a min. Okay? If it goes from negatives to positives, you have a min. If it goes from positives to negatives, you have a max. Why? Because negative tangent slopes mean my function's going down from left to right. Positive tangent slopes mean my function's going up from left to right. Okay? Now, the next thing that's very key is understanding when and how easily it is to see when something is positive or negative. Okay, so this is just kind of a side question. This is not related to finding maxes or mins, but it's kind of a side question of, hey, if I have a function, how can I figure out when that function is negative? How can I figure out that the signs, like what locations? Do I just plug in random points? No. It's very simple. It's an awesome concept, though. It's very powerful. If I know the zeros of my function. And I know all of the zeros. In between your zeros or outside of your zeros, your function values will always have the same sign. In between these two zeros, all of these function values are negative. Over here, all my function values are positive. Over here, my function values are all positive. So all I need to know is really my zeros and then the sign of 1, 2, 3 points. And I'll know the sign of all of my points of my function. Okay? So if I'm asking you to find when something is negative, find the zeros. Test around it. I'm going to kind of change this up really quickly. Make sure that this is factorable. If I want to figure out when this is negative, I will first find the zeros. So x squared minus 2x minus 3. I get x minus 3, x plus 1, giving me 2 zeros. Right? Now that doesn't answer my question, but watch what I can do. I can create this number line that we've been talking about. And this time I'm talking about the signs of y. The sign of y. Okay? All I need to know is what's going on at 0. 0 is between -1 and 3. I guess this is -1, this is 3. If I plugged in 0 into my original function, I would get a negative value, -3. Well, just by taking what this is, which is called a test point, knowing that this will produce a negative value is telling me that all of the y values between -1 and 3 will always be negative, so long as I found all the zeros. If there's actually another 0 in between -1 and 3, well, then I can't say that, because then I know I'd probably be going maybe something like this, okay? So if I find all the zeros, though, I'm comfortable to say if this is negative, they're all negative. Now, how do I find that? Well, I could plug 0 into this, or I could plug 0 into this simplified factored one. If I plugged in 0, I'd get 0 minus 3. 0 plus 1. I can kind of do that in my head, knowing that this is a negative, this is a positive. A negative times a positive is a negative. After 3, I can test something like 4. And if I plug 4 in here, maybe it's going to be tough to do in my head, but maybe using the simplified one, all I need to know is the sign. I don't even need to know the value. I need to know this is positive, this is positive, a positive times a positive is a positive. Means all my y values to the right of 3 are positive. I test something like -2. This is a test point. And I'd have -2 minus 3, -2 plus 1. This would be a negative times a negative. That would give me a positive. So just by finding zeros and then testing some values, I know that actually when is y negative? When is this negative? Between -1 and 3. Okay? Now this is just to find when a function's negative. What we will be doing is we're going to find when y prime is negative, because that will tell me when y is decreasing. And all of a sudden, it's not going to be sign of y, it's going to be the sign of y prime. And then once we have the sign of y prime, I could say, oh, my original function y is increasing. Then y is decreasing. Then y is increasing, telling me that this is going to be the location of a max of my original function y. This will be the location of a min of original function y, Y is going to be decreasing between -1 and 3. See how that kind of plays out? It's really the same thing as what we did last class as the beginning, just we have one extra step now. We will do this analysis of signs, okay? Let's do our first kind of problem. Here is f prime. The question is, what are the critical points of f? And I'm giving you f prime. I just went ahead and just gave it to you already. We don't even know what f looks like. And then you're going to be able to figure out, are those locations of relative extrema of f? And you can actually, without knowing what f is, just by knowing f prime, you can actually kind of sketch f. So kind of 3 parts. All right, so this is f prime. The questions are asked about stuff about f, but we know to find a critical point of f, it's when f prime equals 0 or undefined. So step 1 is to find these critical points. Go ahead and do that. Very easy because it's already set up for you nicely. Okay, we got that. Now here's the extra step. Create a number line so that you can analyze the signs of f prime, which will tell you stuff about f. Make sure you order your critical points from smallest to largest. Then, using your simplified f prime, this is f prime, you can plug in test points on these intervals, knowing that when x is -2, this is 0. When x is 3, this is 0. You know that these are all positives or negatives. These are all positives or negatives. And these are all positives and negatives by doing quick test points. Go ahead and try that out for yourselves and check your answers with your neighbor. We should have just a plus or a minus in those intervals. Now that's sketching f prime here. We want to sketch f, which we don't know. Now, how do we do it? It's really good just to take easy values, plug it in here. Don't care about the numbers, just care about whether they're positive or negatives. What I like to do is I'll just like pick 4. Sometimes I'll just write here and put in a 4. Sometimes I won't even write it down there. Sometimes I'll just leave it off. But just so that we know, I'm picking 4. 4 minus 3 is a positive. 4 plus 2 is a positive. Positive times a positive is a positive. I like to start on the right too, because positive values, and then I work into the negatives, moving to the left. So between -2 and 3, I like to test 0. So 0 minus 3 is a negative. 0 plus 2 is a positive. This is a negative. That means all of my f prime values between -2 and 3 are negative. That tells me stuff about f. But to the left of -2, let's say -3, This would be a negative times a negative. That's a positive. So immediately after doing that, I can say, okay, f is increasing until we get to -2. Then we know we don't increase or decrease at -2, but right after -2, we decrease. And then we go to 3, and then right after 3, we increase from there. So either going from right there, you can sketch f. And f, the original function, though we weren't given the equation for it, has to look something like this, where we increase, decrease, and then increase. This is going to be this is going to have to be at x equals -2, and this is going to have to be at x equals 3. You might have to sketch f, or just know that we're going from increasing to decreasing. This is the location of a relative max for f. This is the location of a relative min on f. Okay, so we took it a step further, and we found not only my critical points, but what's going on at that critical point, and I can do a decent job of sketching my original function, even though in this situation I wasn't even given it. Well, most of the times we will be given the function. But again, like, what does this look like? Where does it have maxes and mins? Does it have maxes and mins? Is it like x cubed? I don't know. But by doing this analysis of my derivatives around my critical points, I can find these locations of these maxes and mins. And I can see if this critical point is a special critical point, a location of a relative extrema. Okay? So here is just, one extra step from the previous problem is we're going to have to find the critical points, then analyze the signs of your derivative. Go. Derivative of 7x is 7. And you'll be able to factor that. Now, I see a lot of people with numbers as they're doing their test points. You don't have to do numbers. Think about plugging in the number into your simplified derivative and just think positive, positive, positive times positive, 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 negative, positive times a negative is a negative. That's going to be maybe a little bit easier to do than working with numbers. Sometimes we will make mistakes if we do numbers, but all we care about is just if it's positive or negative, not how positive or how negative it is. Go ahead and check your number line with a neighbor. Go ahead and maybe sketch f, what f looks like, maybe indicating the locations where we have this interesting thing. Two numbers got to multiply to get positive 7, so that doesn't work. It's going to be negative 7 and negative 1. Just make sure we're shifted so it's at the spots. Good. Okay, so I find the critical points. I don't have to worry about when this is undefined, fortunately. I factor to solve this set equal to 0. I get my 2 critical points at 1 and 7. But now, let's see what's going on around 1 and 7. I have a 0 here, 0 here. And again, this is the sign of f prime. I usually put that on top of my number line. On the bottom of my number line, I talk about what is f doing. It's not the sign of f, but just what is going on with f. Now again, quick test points. 8. 8 minus 7, positive. 8 minus 1, positive. I like to start on the right. You guys can start wherever you want to. It doesn't matter. 3. 3 minus 7, negative. 3 minus 1, positive. That's a negative. 0. 0 minus 7, negative. 0 minus 1, negative. That's a positive. So again, that's telling me f is increasing till it flattens out, then it decreases till it flattens out again, and then it increases from there. So I must have a max on f at 1. I must have a min on f at 7. So again, if I were to sketch this, I'd focus at 1 and 7, and I could actually go back and plug in 1 and 7 into my original function and find out the specific locations of these maxes and mins. This is something that your book stresses. I actually won't stress this as much as the book. So I just want you to find the x locations of the maxes and mins. But if you think about it, you could do 1/3 minus 4 plus 7. So that's 3 plus 1/3. So 3 1/3, 10/3. You can go and say 1, 2, 3 1/3. That's where we're at there. And then you could plug in 7. I don't know what that is, but you could plug it in. And you know that, hey, I'm going to go up to 1, 3 1/3. And then I'm going to go down to some value at 7, positive or negative, I'm not sure what it is. But there is a max, and there's a min, and I know the locations of it, okay? Your book will always find the locations of the maxes and mins. I don't care so much. I just care about this here, and that this is a max and this is a min, okay? Let's try another one. So really my question is find the x locations of the relative extreme of the function. And then you can, do a general sketch. Three times 4/3 would just be 4, and then this would be x squared. Find your critical points. Examine the signs around your critical points. Nice. This is a great example of how, the previous two ones is like positive, negative, positive. Maybe the other one could have been negative, positive, negative. It's not always like that. We do have situations where the signs do not change. It will be helpful if you use your simplified derivative. Four x squared times x minus 1. Gives you 0 and 1 for your critical points, which means you're going to have to use a fraction as your test point, but that's okay, because you just care about signs. You don't care about plugging in numbers. I like to start on the right. Plug in 2, positive times a positive, definitely a positive. I plug in a half. Well, the 1/2 squared, positive. 1/2 minus 1 is a negative. This is a negative. I plug in negative 1. Negative 1 squared is a positive. So that left term remains a positive. Negative 1 minus 1, definitely a negative. This is also a negative. So that means f decreases. It flattens out here, but then it decreases after there, flattens out, and then increases. Can we try to sketch something like that? Decreases, flattens out, decreases, increases, maybe something like that. Right? Only this is going to be at 0 and this is going to be at 1. And we can actually find those specific locations if we plugged in 0. This is actually going to be 0, 0. Right? Because if I plug in 0, I get 0. If I plug in 1, I got 1 minus 4/3. So that's negative 1/3. Okay? Pretty cool. All right, let's do another one where we have a fraction. Tackle this one. Actually haven't done this one yet, so let's see. This is crazy. You kind of just figure out from x to the fourth minus 1 that you have -1 and 1. You also have 0 in there. You have 0 both from the derivative being equal to undefined and from the numerator set equal to 0. Okay, so after I get that, now comes the analysis part. Now, it's important to know that at 0, your derivative is undefined. This is the first time that we've had that situation. At -1 and 1, those are both zeros. Now, if you look in the original function, you know that you can't plug in 0, you have 1 over 0. What does that tell me when I have a number over 0? What's going on at my function? Vertical asymptote. Excellent. It ends up kind of being an interesting location, being a location that we still need to keep track of so I can include it in my domain, even though it technically is not a location of a critical point because there's no point there. It's an asymptote. Now, I'm going to use this guy here over x to the fourth as my simplified derivative. Because I know x to the fourth will always be positive. That's important to know. It'll always be 2x and x to the fourth minus 1. Okay? Now, I plug in a value like 2. Denominator is positive. This will be a positive. 2 to the fourth is definitely bigger than 1, so this will also be a positive. So I have a positive here. I plug in a value like a half. Well, 2 times a half is a positive. 1/2 to the fourth, if you take a fraction, take it to a power, it just gets to be a smaller fraction. It's 1/2 times 1/2 times 1/2 times 1/2. Minus 1, that's definitely going to be a negative. So this is a positive times a negative divided by a positive. That's definitely going to be negative. And then I look between 0 and -1. So now we have a negative from 2 times x. And then -1/2 to the fourth. Well, that'll end up being a positive value, but it will be small. When I subtract 1 from it, it will also be negative. And that's divided by a positive, so this is actually positive. And then to the left of -1, -2, this will be a negative times a positive over a positive. That'll be a negative. Okay? What is this telling me? Well, f is going to decrease, then increase around -1. This is going to be a relative min. It'll decrease, then increase at 1. This will also be a relative min. So what could it look like? I don't know. Decrease, then increase. Decrease, then increase. Maybe something like that. Let's find out. Let's graph it. X to the fourth plus 1 over x squared. Very good. Okay. All right. the power of signs of derivatives can show me what this is going to look like. Here's another question. This is a trick question. I want you to read this question carefully. Write the question down as well carefully. You will not do this question like you did the last three. Discuss with your neighbor what you think you should do to tackle this problem. My advice would be to go back into your notes and look at when we were talking about when things are increasing. What do we look at? All right, Mr. Schoonmaker, what do you think? Right. Something is increasing when its derivative is positive. We're not going to look at the values of f prime and see if they're like increasing 2 to 3 to 4 to 5. We're not going to do that. It's actually going to be tougher than by taking the second derivative and seeing when that's positive. How do we figure out when the second derivative is positive? Find the zeros first, and then analyze the signs around your zeros. Perfect. Excellent, Mr. Kobayashi. Go. A couple ways you can write it. You can say x is greater than -1. Please do not include -1 because we are neither increasing nor decreasing at -1. You could also write it like that from -1 to infinity. Okay? But that's the idea. Okay? We can look at when velocity is increasing, when velocity is decreasing. Not by looking at values of velocity, but by looking at the values or the signs of its derivative. Okay. Sometimes, and lots of times in this class, you will only be given a graph. But the graph is of f prime, and the questions will be about a function that we don't know, f. We have no information about, but we have its derivatives graph. Okay? So, from looking at this graph of f prime, you should be able to tell me the critical points of f. And you should be able to tell me where f has relative extrema. Start by finding the critical points. Discuss what you think your answers are with a neighbor. Go. If you are telling me that the critical points are at -1 and 2, you're wrong. Not at 0. Yes, the values when it equals 0. Yes. What are the values? Okay. So we're actually looking for critical points of f on when f prime equals 0. Well, we're looking at the y values of f prime, the function values of f prime. When is f prime 0? Well, when the y value is 0, when we cross the x-axis, we get those values, right? It's just simple. The question is, when are the critical points of f? Well, you know critical points when f prime is 0. So, boom, you got it. But now, can you create a correct number line for f prime that will tell you when f has a max or a min? And could you then sketch f by just given the graph of f prime? Values of f prime. We're talking about the values of f prime, not the tangent slopes, the values. When you're above the x-axis, these values are positive. When you're below the x-axis, those values are negative, right? Well, between negative infinity and negative 3, these values are negative. Between negative 3 and 1, all of those values are positive. Between 1 and 3, like at 2, whatever this y value is, maybe it's negative 2. That's a negative value. And after 3, positive. That's telling you what f is doing. So if you wanted to, f would go decreasing to increasing to decreasing to increasing and look something like that. And maybe, you don't know exactly where it's located. For right now, you actually don't know if you drop down more or less. This is just a general sketch, a general idea. Something like that maybe even, whatever, okay? Got it? All right, good. Well, same question for this graph of f prime. I want you to tell me the critical points. What are they? And then tell me where we have relative extrema by creating a number line for f prime. This is the critical points of f given the graph of f prime. And then go ahead and do a decent sketch of f. Shake hands with a neighbor. So we know that at 0 we have a max, at 2 we have a min. You can do a decent job of sketching. It should make sense. Think about this as being a quadratic, an x squared. You know that the original function had to be some sort of x cubed. But this goes a little bit further and tells you that, you know, it's an x cubed that has a max at 0 and a min at 2, something like that. You know, is it just like this? I don't know. You know, we're just kind of sketching. All right. Let's do that. This is the graph of f prime. Where does f have a relative max, and when is f increasing? Go. Can you do it without creating a number line? Can you do it without creating a number line, without sketching? If you check, create a number line. Maybe don't sketch. You can just literally say f is going to have a max when f prime goes from positive values to negative values, right? Where does f prime go from positive values to negative values? At 3. Right? I don't need a number line for that. When is f increasing? Well, we know that's when f prime is positive. When's f prime positive? -4 to 3. Okay? Can be confirmed if you just created this guy if you wanted to. -4, you have f prime is equal to 0. 3, you have f prime is equal to 0. Just goes from negatives to positive to negative. A lot of people get scared about this sharp point. Don't be scared about sharp points. Okay? They are concerning to us that when a derivative is undefined when we're talking about our original function. But that's okay. We like those points because those could be locations of maxes and mins. If this was just f of x, well, you would look at f prime being positive, 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 undefined, negative, negative, negative. That would be the location of a relative max, okay? So we don't exclude answers if we see sharp points. Everything is fine. Just go with it. Trust in what you're trying to find and find it. All right. Good job. Thank you.